So I undertook a much too ambitious goal in this talk because string theory is full of surprises, successes, and many challenges. And I decided I would start at the beginning and give you some of the context of the history of string theory, as well as how it fits into the search for understanding the real world, as opposed to the mathematical world. And that is quite a overly ambitious task, as you will see. I was also challenged by the fact that all my old slides on string theory from years ago You can hear me, right? You don't laugh at my jokes, so I'm confused. So I'm going to start at the beginning with the birth of string theory. String theory is almost 60 years old. It's a long subject, perhaps is still in its infancy, I believe, but it goes back to 1968 when the dual resonance model appeared. This was not a theory of strings. It rather was an attempt to construct a model of experimentally, but not which was believed by many to be impossible or not the right way to proceed, but rather the idea of the bootstrap, which has appeared, continues to attract people's attention nowadays as well. So the idea was being pursued, especially in Berkeley, where I studied, was that you should try to construct a S matrix, the amplitudes for the scattering of hadrons, protons, neutrons, pions, so on, simply based on general principles. General principles being not axioms, but assumptions that we make about the fact that these probabilities we calculate should add up to 1. Analyticity, which is, we believe, analyticity of the scattering amplitude. Causality, the fact that events in the future are caused by events in the past and not vice versa. Crossing symmetry of scattering amplitudes is a function of the complex analyticity of the variables that the amplitudes depend on, energy, scattering angles. Consistent with all these principles, it will be the unique amplitude that describes the scattering of strongly interacting particles, nuclear particles. This was a pretty straightforward program, very difficult to solve, impossible, certainly at that time. And it was therefore a great surprise when a very simple formula or a similar amplitude related by causing the T amplitude, T being the scattering angle in this channel and the energy in this channel. The Veneziana amplitude was a guess for a function which had poles in this channel or poles in this channel, and Regge behavior for large S fixed T or large T fixed S. This is obviously symmetric under S and T interchange. This, of course, was not a unitary amplitude. Okay? The probabilities you calculate for two particles, or very quickly this formula was generalized to amplitudes for any number of particles to any other number of particles in terms of sums over poles. In terms of the energy, or in one channel or the other channel, poles with polynomial residues, which meant a finite number of spinning particles of mass. S is the center of mass squared in this channel, T center of mass squared in this channel. The residues are polynomial. Expressing the particles in either this channel or this channel. Of course, particles can't be infinitely narrow. A particle of high mass can decay to particles of lower mass. So this was an ansatz, if you want, for the tree amplitudes, the lowest order amplitudes which need to be corrected, and they can be corrected and to implement unitarity, as we know in quantum field theory, by constructing loop amplitudes. Remarkably, this was just a mathematical formula. Strings never appeared. And yet, within a period of a year or so, a year and a half, this was generalized not just to not just the 2-to-2 scattering, as illustrated here, but all possible scattering amplitudes. Unitary coupling. This was quite remarkable that one could move so rapidly, and it was only a few years later that it was realized that the amplitudes of these scattering amplitudes were actually what you would calculate if you tried to quantize an extended object, an open string or a closed string, using the action that describes the motion of an open or closed string as with a weighted over all possible trajectories of area of the world sheet that a string creates as it moves in time. Much like in quantum field theory, the free particle moves in such a way, classically, to extremize the length of the path, and quantum mechanically, we sum over all paths weighted by the action, which is e to the I times the length of that path. Then realized that relativistic strings. String theory, so this is a slide of mine from many years ago, which wasn't destroyed by the updates, where I said that string theory is a radical, it appeared, modification of the principles of physics. Very exciting to make a modification of the basic principles of physics. Very difficult to do because we know so much that most attempts to really change the basic rules are disastrous. They contradict either experiment or logic. And this seemed to be one of them, string theory. Particles are replaced by strings unchanged. The way to think about the experiments we do at the LHC, at colliders, is we sum over all possibilities where particles collide, create other particles, which create other particles, and so on. We sum over all possible paths weighted with a phase factor, which is given by the quantum field theory action. And to some extent, dual resonance model, Veneziano formula, string theory is doing the same thing, except that we replace a line and the length of the area of that. We describe by exchanging other particles in Feynman diagrams, we try to do the same thing with interacting strings. So this appears to be a totally different way of doing physics. We're saying that the fundamental constituents of matter are not particles, but extended objects, either closed or closed, like here, or open strings. Which is one of the great surprises, if you want, in making this extension. And that has to do with the nature of interactions. If you regard scattering amplitudes as sums over paths for particles, and you want them to interact, not just move freely, you have to consider events where two particles A and B can meet and form a third particle. That looks rather singular, and in fact, when you try to implement that in quantum field theory, you have, first of all, a variety of choices. One of them being, if two particles A and B interact, they might form two particles or three particles or just one. That corresponds to various terms in quantum field theory in our description of interaction. In the Lagrangian of is somewhat arbitrary, and you can assign a probability for A, B goes to C at your will. And that is where, in quantum field theory, much of the arbitrariness in our description of nature comes in. So in our quantum field theory theories of elementary particles, there are many parameters. The masses of these particles, A, B, and C, as well as the coupling constants that measure the probability amplitude for A and B to form C, which spin, so on. In the case of strings, that's not necessary, it appears. You could try to do that and you'd run into disaster. For example, you could try to imagine that the interaction occurs when two strings overlap. That would cause immediate disaster, non-locality, okay, as well as an infinite number of parameters, adjustable parameters. Join to form a closed string C. And if you draw this picture, this world sheet that describes this event in Euclidean imaginary time coordinates on the world sheet, there's nothing singular or happens when they join. There's no interaction point. And at every point here, you just moves you forward in time. The fact that they've joined together is only really noticeable much later on and is a topological feature of this pants diagram. So there is no choice to be made at all. Once you know that the free string is described, the motion of the free string is described by the exponential, the phase factor proportional to the area, then you know that is a remarkable feature of string theory, one of the reasons it's so powerful and attractive. So string theory, for me personally, seemed enormously exciting, and I worked on it with some of the young physicists, now great founders of string theory, John Schwartz, André Naveau, Joel Shirk, in Princeton in the early 70s. It was truly amazing. It started between them. All sorts of surprises happened. In the history of string theory, 60 years ago and today is a history of surprises, things one never anticipated or dreamed of, which were forced on one by exploring the mathematical structure, starting with a Veneziano amplitude. For example, it was discovered that this theory made no sense unless you were working in 26 space-time dimensions, which we don't have around us, so we were certainly not looking for a theory in higher dimensional space-time. How did we discover that? Well, actually, people were, as I said, were trying to perturbatively correct in the number of handles, the genus of the world sheets that unitarize the Veneziano amplitude. And these amplitudes, singular point, like the point in a graph where two particles meet to form a third. That is that coincidence of those space-time points when an interaction occurs is the origin of the ultraviolet infinities that happen in quantum field theory. No such thing happens with the pants diagram. But what we discovered in unitarizing singularities that destroyed unitarity We were confused. Lovelace saw that if you worked not in destroyed unitarity, but poles. And there were poles in a different channel with different quantum numbers. In fact, there were poles in a channel which had none of the quantum numbers that we associated with the ends of the open string. They were, in fact, in 26 dimensions, spin 2 elementary particles, otherwise known to us as gravitons. So, in the world sheet theory of the scattering amplitudes that describe the scattering amplitudes of strings by Naveau and Schwartz and Ramon, who tried to include fermions into the game, as we have to. There are fermions, most of, in fact, electrons and quarks. And when people tried to introduce fermions, they introduced anti-commuting coordinates on the world sheet, essentially supersymmetry in 2 dimensions, and that was one of the motivations for the discovery and the utilization of supersymmetry in other theories. In addition, another time of Minkowski, and there was hope model, you would actually find that it only made sense in 4 dimensions. This was somewhat mysterious, perhaps less mysterious. Another big surprise, which I already alluded to, is that the theory only made sense if you included gravitons, which automatically leads to, at least at low energies, to Einsteinian gravity. So, as Ed Witten once said, that string theory has had an experimental success. It predicts since Newton, so that's not exactly a prediction. But gravity appeared automatically. Now, I was really interested in what was going on in high-energy physics, where it was discovered most dramatically at SLAC around the same time, 1968-9, that it looked like, when you looked at the proton with electrons, scattered electrons, a microscope to see what was going inside the proton, it was discovered that the proton looked like it was made out of fractionally charged particles, which were barely interacting when you observed them at short. One thing was obvious from string theory. At least naively, where the interactions are very smooth, there are no divergences, and there's no way that can describe these experiments, at least naively. So that led this later acknowledged discovery of quarks and their almost free behavior at short distances, led me on a journey to understand that observed feature of nature. And remarkably, after a search for all possible theories that could exhibit this behavior, my first student and I unlike any other theory, to explain the slack results, one had to look for a not abelian gauge theory of the strong interactions. There really was only one choice given everything we knew, the number of colors, which determined the gauge group, and the existence of quarks, and so on. So that's when QCD emerged, or appeared, and and for many, physicists began to resolve the issue: how do strongly interacting particles interact? What is the theory of the nuclear force? In the case of the nuclear force in QCD, in a theory not based gauge theory, the vacuum forces the flux between the charged particles to be squeezed into a tube. That not only turns out to explain why the force decreases when the particle quarks, here quark and an antiquark, say, are very close together, but also that the force does not decrease as you pull the quarks apart, leading to a linear potential, a constant force at large distances, which might be, we thought, a mechanism for the confinement of quarks within the nucleons and other hadrons, so that we've never observed fractional charge in the real world, never observed quarks. And that theory has turned out to be quite, I could talk about that for at least 2 hours, quite successful, tested with other colliders, but as theorists, most satisfying that we can actually calculate the masses of the hadrons with almost no parameters, essentially no parameters. The light quark masses do make a slight few percent difference, with precision which is now, after 40 years of calculation, it really required 10 in our ability to calculate using lattice realizations of QCD, taking the continuum limit. It is a factor of 1 billion in the power of computers over the last 40 years, and a power of 1 billion in theorists' understanding of the dynamics of QCD, the chiral phase transition, finite size effects, algorithms, improve the... It's a bit staggering to realize that in order to go from a qualitative argument about what the masses of hadrons come from in QCD to less than 1% precision requires such an enormous increase in our computational power. But it works. Elementary constituents of matter, consisting, as you know, of three families of quarks. These are inside the nucleon. These are heavier quarks. The electron and the neutrino, which are the doublet, the two colors of an SU3 gauge group that also describes the weak interactions. In the case of QCD, the quarks are confined. In the case of the electromagnetism, well, they're not confined. We have long-range macroscopic electromagnetic interactions, and we can ionize atoms. Three of the weak interactions, the SU2 non-abelian gauge symmetry, is Higgs, and the forces are screened, only act at short distances. And so the standard model as far as the forces go is described by three gauge interactions based on three gauge groups, 1, 2, 3, conveniently. One charge is electromagnetism, two charges is electroweak interactions, three charges broken, electromagnetic unconfined, and strong gauge theories. Plus, of course, one needs, and now been verified to some extent, the Higgs sector, which breaks the electroweak symmetry, produces masses for the chiral matter, the electrons, and presumably the neutrinos. And this seems to work over the last 40 years in literally thousands and thousands of experiments, with so far. But there were a few stubborn, insightful people who continued to work on string theory, not as a theory of the strong interaction, not as a theory underlying the standard model, but perhaps as a theory of gravity, since gravity in string theory was unavoidable. So that's not to say that the standard model is complete in any sense. There are many issues that force us, because they're observed and measured in the real world, that are not described so far in a definite way by the standard model. For example, neutrinos have been observed to have masses and to mix, therefore, and which is left-handed, a Majorana particle. Particle could be its own antiparticle. It's called a Majorana particle. We don't know. Most of us suspect, for reasons I don't have time to go into, that it probably is. But remarkably, over the last 40 years, this experimental question is, which can be decided by observing neutrinoless double beta decay, where the neutrinos produced in beta decay annihilate and are not seen, in which case neutrino would be its own antiparticle. We simply don't know, although many of us suspect that it probably is. The universe is made up of particles, electrons excess of electrons over positrons and an excess over baryons over antibaryons, of quarks over antiquarks. And yet, presumably, that wasn't the case at the beginning, whatever the beginning means. Why this asymmetry? It's observed. We know what the excess is in the real world. We'd like to calculate it. So far, we haven't been able to do that. It's partly connected to whether, to the properties of neutrinos, perhaps. Astronomers discovered particles that we'd never seen in the laboratory. Dark matter, most of the matter in the universe is not, we don't know what it is. It's not been seen in the laboratory or in cosmic ray, and the many different attempts to see it. This is one of the most pressing questions in particle physics. What makes up the dark matter? And we don't know. There are many, many, many possibilities. Cosmic acceleration. We astronomers, cosmologists, have discovered that the universe has an although that's a bad term, it really is. If you want to ascribe it to the vacuum, it's the energy and negative pressure of the vacuum. Einstein's cosmological constant, which has now been observed, much to many of our that was a big surprise. There's some indications today that it might be decaying. Hopefully that's the case. That's what string theorists would like and kind of predict, maybe. So these are experimental challenges. There are also theoretical challenges that have been around since the Standard Model was completed. Well, unification of the forces, which I'll get to in a moment. In other words, you would think it would be many, many orders of magnitude heavier. There's no reason that we know of. Supersymmetry was so attractive for so many years because it seemed to explain both dark matter and the hierarchy of scales, and perhaps give stronger evidence for unification. And finally, the properties of the quarks that we have to put in and can't calculate in the Standard Model, the Higgs couplings, the masses of the quarks and leptons, have all sorts of patterns, and we've been trying for 50 years to explain those patterns, calculate those masses, mixings, unable to do so. And then, from a theoretical point of view, extraordinary and vacuum energy are deep theoretical mysteries of which we really have no understanding. But one of the things that drove us to string theory was the realization shortly after the completion of the Standard Model, around 1966 or so, we had this theory, which we know now works very well, of the standard forces in the particles. And so theorists can extrapolate. Theory actually, because of asymptotic freedom, becomes much simpler at high energies than it is at low energies. So you're going to keep extrapolating. And the remarkable thing that was discovered, and still is true, is that the forces appear to come together in strength, unless there are lots of new things in between, which there could be, at a scale which is very, very high energy or short distance, and within an order of magnitude or two, all the forces we observe should be unified, maybe from a big gauge group, which is broken down, easy to imagine, but together with gravity. Gravity is a very weak force at low energy, 40 orders of magnitude less than the gauge forces inside the atom, but the charge of gravity is mass or energy. Decrease. Well, 15 orders of magnitude, shorter distance, greater energy than where we currently observe. So, to me, that's an indication, clearly, that the forces which fit together so nicely as gauge forces, the multiplets of matter that we've discovered fit together in a unified gauge group, which is SO10 or SU5 or E8. No evidence over the last 50 years for anything else here. Even supersymmetry, which string theorists love, solves many problems. Maybe it's there, but so far, no evidence. And if we have to include gravity, we better try to imagine we have it. So QCD also illustrated that it wasn't an accident that string theory or the dual resonance model was discovered in a phenomenological attempt to explain the strong interactions. Because in QCD, when you pull the quarks apart, you create a flux tube, which is kind of a flat, a fat string. And some of the features of Regge trajectory. So string theory really emerges from QCD, we understand. And at the beginning, people considered open strings, these flux tubes, with quarks at the end, so they put in charges at the end of the strings. And today we understand, at least in this qualitative sense, gauge theory and confining gauge theories are somewhat equivalent to, that once you have open strings, you have closed strings, you have gravity, means that if we want to unify a theory of standard model in which open strings are these anti-quark flux tubes, and that is somehow equivalent in some way to string theory. Open string theory, that means that you need closed strings, which means you need gravity, and adds, if you think a la string theory, additional theoretical strength to the idea. And that at least gives a way of approaching quantum gravity, because Einstein's theory is notoriously difficult to quantize, and in terms of our understanding of quantum field theory, looks inconsistent, looks non-renormalizable, looks like you would have to introduce an infinite number of parameters to calculate quantum corrections to Einsteinian gravity. Many general relativists believe that that was the way to go, not particle physics. Quantum gravity at short distances undergoes quantum fluctuations and is still by far the one of the strongest motivations for connecting string theory to the real world, because we have to connect it to quantum gravity. So, if that's the way to go, we could conjecture, as did over the years, that string theory is the way to go, and particles can be viewed as vibrations of a superstring. It's an incredibly unifying idea. There are many. So, string theory reemerged. My view is a theory of unified particles and gravitons, but certainly as a quantum theory of gravity. And because it has no UV divergences, it's perfectly finite, it at least proves, contrary to what many general relativists thought, that quantum mechanics and general relativity are mutually consistent, at least in a perturbative sense. The quantum corrections to the motion of planets around the Earth, though extraordinarily small, are at least not infinite, where space-time itself is fluctuating beyond control. That's been one of the major directions, even more so today than it was 40 years ago, for exploring string theory. It enables us to think about the fate of black holes, which challenges quantum mechanics even, for the case of very strong gravitational fields, and might allow us to address the origin of the universe, which challenges everyone, including, so far, string theorists, and suggests that space and time is much different than we naively thought, in many ways. The first manifestation of this was the realization that string theory only made sense in higher dimensions. You wouldn't see the extra dimensions. This was already contemplated by Kaluza, and Einstein loved this idea once he and his followers realized that space-time is dynamical, so it becomes a dynamical question whether there are other dimensions or not, an experimental question. You have to. And in fact, it seems that there must be, according to string theory, more than 4 dimensions of space-time. The superstring must have 10 dimensions, gravity in 10 dimensions, which is such a nice dimension for supergravity, could be removed by the Green-Schwarz mechanism. It became possible to imagine a consistent compactification of 10-dimensional string theory, either the original versions of string theory, type 1, 2, A, B, and the heterotic string, which we discovered as a possibility of realizing Green-Schwarz mechanism. And it was very exciting. The heterotic string had a built-in gauge group, which could naturally lead to the standard model. There existed nice Calabi-Yau manifolds, which could reproduce the number of families that we observe. And the remarkable thing about determines many of the things that it seems that quantum field theory is unable to do. So, the nature of the forces. Why are there gauge forces? Why is it SU1, U1, SU2, SU3? What are the values of the masses of the elementary particles? In quantum field theory, it's very hard, certainly haven't succeeded in imagining there would be some kind of principle that would answer these questions, and now it's reduced to geometry. Amazing. All these questions that standard model can't answer are reduced to geometry. So you just have to find the right geometry, and boom, you could make predictions. Not so easy. You'd have to break supersymmetry, a lot of problems. Certainly more than 10 to the 500 manifolds you could compactify on. And there's no principle that deciding which of these manifold of manifolds and try to find a nice one that agrees with the standard model and then makes new predictions. That's how you proceed in science. But how are you going to possibly? And by the way, in all of these, you have to calculate the cosmological constant, which is 120, appears to be so small. It's almost measures zero. So you're very unlikely to be able to agree with nature. In my own view, and useless speculation. The anthropic principle here must be the one that can support us, and there's no physical principle or predictive power. Yep, that's a sign of giving up, in my opinion. But one thing that we've learned in trying to understand the properties of geometry from string theory is very deep questions about space-time, which have gotten only deeper. We have a background, continuously go from one manifold to another. You can change the topology continuously without any disaster. And it's even true that the number of dimensions, in some sense, is not fixed. It depends what question you're asking. Sometimes it's worse. It's useful to think about working in 10 dimensions. Sometimes it's really space-time, or what is really geometry. There are different views of this. Mathematicians tend to think about geometry as fundamental. Personally, I believe that physics is fundamental. So mathematicians like to imagine that physics will emerge, come out of understanding geometry. Personally, I think geometry is much more complicated than they imagine, and it will come out of physics, but the two are deeply related. We believe now, in some sense, that space-time is emergent. What does that mean? Well, we really don't understand at all, or just beginning to understand. The best is that we have dual descriptions, separate descriptions which describe the same physics, but geometry is very different in either of those descriptions. Gravity, of course, in that sense, gravity is emergent as well. And we indeed have cases now where gravity emerges or can be described by non-gravitational theories. Gravity, after all, is a dynamics of space-time. So if space-time emerges, so does gravity. But we really don't understand in a fundamental way if space-time is truly emergent, by which I really mean that there is a a fundamental description of physics in which the various pictures we get, dual pictures we get, can be derived. And since space-time kind of emerges, space-time is not a concept that's in that basic description. And, well, we have some progress in that based on what was the next and perhaps the most recent surprise in string theory, which has had great successes, of the duality between, in string theory language, open strings that end on a brane and closed strings in the bulk. In a more direct case of ADS-CFT, which has dominated the field for the last 30 years, started out with a explicit description of string theory in anti-de Sitter space, which is kind of putting gravity into a box, which has a boundary where you can sit and do observations. And the discovery of Maldacena and Polyakov, Gubser, and Klebanov about 30 years ago was that there's a dual description of exactly the same physics, either in terms of string theory, at large distances, gravity, in the 5-dimensional space, times a sphere, but it's not important. It's really 10 dimensions, dynamical theory of strings, and an ordinary quantum mechanical relativistic theory on the boundary, which has no dynamical space-time, rigid geometry, no quantum field theory with gauge interactions. This theory is very standard, close, small deformation of the standard model to some extent, gauge dynamics, and this is quantum gravity string theory. Remarkable correspondence, and incredibly powerful because you can learn about quantum gravity and string theory from ordinary quantum mechanics. You can learn about ordinary quantum mechanics for strong coupling from Einstein's equations and string theory. And that has taught us a lot. For example, has revived the hope that we can actually calculate the properties of these flux tubes in QCD. And I believe eventually we will do that. It's very difficult to derive a string-ish theory description of quantum chromodynamics, large distances where the forces are strong. Very important practical question. But we can also really start to try to understand what does emergent space-time mean. That's difficult. We have many examples in ADS-CFT and its generalizations in which some or all of space is not fundamental in the one way of looking at it and emerges as a classical, large distance, classical on the string theory side, large n, approximation. So we can see how space-time emerges or can be described in terms of a non-geometrical starting point in a dual description. But time doesn't really emerge in these theories. Space-time does, but not time. And we really don't know how to imagine. So we can imagine formulating a description of everything with no space. But we have no idea what it would mean to try to formulate an underlying description of reality without using time. Because physics is about time, it's about predicting the future. So how do you formulate physics without time? We have discovered that there's a deep and exciting and developing connection in these dual formulations between the structure on the field theory side, conformal field theory side, structure of quantum states. And on the other side, the geometry of the dual space-time. So it could very well be that there's an underlying formulation beneath everything we have learned that does not have any geometry in it, and in which somehow from the quantum nature of reality, space and time emerge. That would be quantum mechanics leads to geometry, not the opposite. Nowhere has this proved more valuable in that first paradox that we have in classical relativity, that of black holes. Hawking claimed early on, when he discovered that black holes radiate and disappear, that since stuff can fall into the black holes can radiate, be wrong, in general, by these dualities. Because in the dual theories, black holes are quite physical objects, similar to quark-gluon fireballs, which eventually radiate without losing any information. And Hawking agreed that this was a demonstration that string theory and ADS-CFT duality in general means that information is conserved. The second big paradox, where one hopes that string theory will help, would be the beginning of the universe, the Big Bang, about which we know nothing, fundamentally. Some happened, somehow theory, which general relativity, there are singularities, nobody knows what to do. In string theory, there are no singularities, we still don't know what to do. And I think part of the reason is that this is a totally new kind of problem for physics. If you have a theory of gravity, of quantum gravity, it describes the universe. The universe is simply the space-time history. That's the answer to understand, to write down a solution for the universe. It's a history which has a beginning, whatever that means, might have to describe a boundary if the universe has a boundary, probably doesn't, and the end as well. And what are the rules? Well, this is a kind of question that physics never had to answer. We assume initial conditions, or we try to show it doesn't matter what initial conditions we put in, and then we can predict the future. That's the job of physics. But and it's not at all clear that physics can do this. It's never had to. So it's a new kind of question. It's now become not a religious or philosophical question, but we want to calculate. We don't know the rules. So what are we working with? What is our current ideas about the framework of theoretical physics? Well, it certainly includes quantum field theory, which is extraordinarily successful in constructing the standard model, a standard theory. Then there's string theory, which originally we thought was a radically new idea, different than quantum field theory. But now we realize that, first of all, string theory must reduce in many situations to quantum field theory, but even worse, in ADS-CFT, it's equivalent. There are two descriptions, the same physics, one using quantum field theory, one using string theory. They agree, we believe, mathematically exactly. So These really are not different frameworks for physics, but rather part of some bigger framework that includes both. Quantum field theory really isn't a theory, it's a framework. Within that framework, we choose model theories, actual theories that we can calculate and predict, but they have a lot of parameters. String theory, there are no parameters. All parameters are dynamical. Should be able to calculate everything in terms of three-dimensional scales of mass, length, and time. But there are at least 10 to the 500 vacua solutions. So I kind of believe that all these two, string theory and quantum field theory, are limiting descriptions of some underlying description of nature, in which space-time is kind of an approximation, good in that might allow us to actually, one, we would like to unify, but even more, we would like to pick out the quantum theory, like the standard theory, that determines all the masses of the quarks and the mixing angles and the fine structure constant. We should be able to calculate those. What's the principle? And what picks the theory from the framework? Same question arises in string theory. Parameters are all dynamical. They could be fixed by some dynamics. But there's so many possible starting points. What picks the vacua of string theory? These might all be related, I believe, to cosmology. So the answer to particle quantum field theory is, well, quantum field theory is part of string theory. So if we find what the principles are, but I suspect that that might be related to the issue of uniqueness, because all of those solutions of string theory, Labiao, compactification, supersymmetry, breaking, they're all sick because they all break down in some way at the beginning. That's true. Nobody knows how to describe the beginning. And they all probably break down in different ways at the end, which, except for flat space and description at large times, is pretty sick. You can either have a big crunch or continued accelerated expansion, which makes all observers causally disconnected in the future, both of which are crazy, it would seem. So it could be wish and a dream, not a real suggestion. But I believe they're related. And of course, we're never going to do that without understanding the beginning and the end. And for that, I have no doubt that we have to change the question and really understand the nature of space-time. There's a lot of progress in recent years about understanding the nature of space and time inside black holes, resolving the information paradox. But the universe and the kind of singularity that occurs, if we extrapolate to the beginning. I love to encourage the young people in the audience who want to engage in this speculative kind of physics, mathematical physics, that the successful attempt to derive delicate laws of nature along a purely mental path, which means there's not going to be much experimental help in the next few years about the beginning of the universe or the nature of physics at the Planck scale. We've learned, unfortunately, over the last 40 years, that what could have happened and told us so much hasn't yet happened. Nonetheless, if you follow a belief in the formal unity of the structure of reality, you should be encouraged to continue in this speculative direction, but the dangers of which everyone should keep in sight who follows it. Einstein did this after his great successes, the last 30 years of his life, and was a complete failure. But don't give up. So I have gone, I think, an hour and a half. We're going to continue with questions, but I'm going to end here.
I really like it, but I would say that I think you were somewhat exaggerated that Krabiao has more than 10 to the 500. 10 to the power 500 number of Krabiao. I think
there are more, right?
I think it's exaggerated.
Exaggerated?
Yeah.
There are fewer.
If you assume the 3 generations, they reduce to a very small number.
Look, in reality,
Yeah.
we believe
Yeah.
that there are an infinite number. Let me finish. Yeah. There are an infinite number of string theory backgrounds. In fact, type 2 string theory in flat space is completely, has a marginal parameter, has a coupling constant. Yeah. So there are an infinite number of such theories. Yeah. We understand them at low energy. Yeah. Because the duality, S-duality, we understand them at strong coupling, weak coupling. No indication of any problem, except that that's not the real world.
Yeah, true.
So as far as string compactifications go, there are an infinite, continuous infinity, not all of zero, all of one number of possible universes, none of which look like the real world. What principle picks out?
Yeah, I agree. But you want to fix the topology of Krabiao there, I don't think there are that many.
They're finite.
Yeah, they're finite.
How many?
Well, we don't know, but I think...
so what's a lower bound?
Well, I mean, depends what constraint you want to put in. For example, you say that a free family, that means the oil number is plus or minus 6. There would be maybe less than 100 of them only.
No, but flux compactification.
They're flux, then you put in all those, but they also can be computed.
No, but they're also string background. They're string solutions.
Well, let's not compute the debate here, but I think it's much less than
anyway,
what you think. Okay.
Anything bigger than one, I have problems.
We shall have a different person in charge of the Q&A. So.
Okay, thank Professor Yao. Thank again, Professor Gross.